So in this section, we are graphing linear inequalities. Or later on in the section, we wind up graphing absolute value inequalities, but it's basically the same thing. The first thing you want to do, and this isn't necessarily in the book, this is my guidelines here. Write it in slope-intercept form. Put the equation or in the inequality in slope-intercept form using your usual rules when dealing with inequalities. And of course, the usual rule that we have to watch out for with inequalities is when you multiply or divide by a negative number. That flips the symbol. So remember that, because those pop up too. Once you have your inequality written in slope-intercept form, then determine the boundary type. The boundary is a vocab word. Boundary is just another name for where the shaded region ends. So in other words, where the shaded region ends is pretty much this line that you drew in there. So the boundary is actually the line that you draw in before you shade. Shade the half plane. That's another vocab word that we have. The half plane is, if you have a plane, if you think of this as being an entire plane that extends in every direction forever, this line right here, no matter where it is, cuts that plane in half. So we have one half and we have the other half forming the entire plane. So the half plane is just the half that we shade on our inequality. And the way we find our half plane that we're going to shade is by using a test point. So once you graph your boundary line, choose a test point in either region, plug the test point into the inequality. Like let's say I picked this as my test point, 0, 0, for this particular inequality. I would wind up with a false statement. That would mean that this point is not a solution, which means that every point over here is a solution. So that's why you would shade this. If you wind up with a true statement, like if I pick this point right here, that would lead me to a true statement, so I would shade this region. Okay? Notice the difference between these two. Both of these red lines are boundaries, but one is dotted. Why would I draw a dotted boundary? Yeah, the inequality itself, y is less than or y is greater than, is going to be looking like that. Less than or greater than. Over here, this is going to be solid because of the equal to that would be underneath the symbol. So if you see a symbol that says just less than or just greater than, you're going to have a dotted boundary line. Greater than or equal to or less than or equal to, you're going to have a solid boundary line. And it turns out that there's a shortcut here. The reason we can use the shortcut is because we're putting these in slope-intercept form. The shortcut does not work if you're not in slope-intercept form. What you can do is look at the inequality itself. If you have y is greater than, then what that means is you're going to take all the y values that are greater than the boundary line. Here's my boundary line. Greater than would be above. You can think of greater as being more than or above, less than being below. And with the way the plane that I drew the arrow in right here is the region that I shade. So that's the shortcut. You don't have to do a test point then. But this only works in slope-intercept form. On this one then I have y is, this is a solid line, so it's going to be something or equal to. And I shaded below, and below would be values that are less than. So my inequality in this case would be y is less than or equal to something. So those are the big points that we picked up from Algebra 1 when we did this chapter. First of all, the dotted line or solid line. Second, which way do you shade? And we always shade either above or below the line. We do not shade to the left or to the right. That has no meaning. It's above or below. So a couple practice problems. We have y is greater than 3x minus 1. It's already in slope-intercept form, so we can go ahead and graph it. I graph it by plotting my y-intercept first, which is right there. And then my slope is 3. So how do I graph a slope of 3? Good. Up 3, 1, 2, 3. And then to the right one, remember that a slope has a rise and a run to it. That's 3 over 1. So I'm going to put some more dots on there just so I get a nice accurate line. Up 3 over 1. Or I could go down 3 to the left 1, down 3 to the left 1. Okay, so I have my dots in there. Now what? It's a dotted line because of the inequality saying greater than, not greater than or equal to. So make sure you get that dotted line in there really well. Again, accurate is better, especially in the next chapter. This still has arrowheads on it. It is still a line. It still goes on forever. Now I just have to figure out which side to shade. The symbol says greater than, so I'm going to go to my boundary line, and I will draw an arrow that is greater than my boundary line, which is above my boundary line. And now my arrow went into this half plane, which means that that half plane is my solution. So I will shade that half plane. There's my solution. Alright, the second one, we are also already in slope-intercept form, so I can go ahead and graph that. My y-intercept is 1, and then my slope is -2. So how do I graph that? Down 2 to the right 1, over and over, until I'm through my grid. Or I could go up 2, left 1. There we go. And what kind of a line will I have here? This one's solid because of the fact that we have or equal to in our inequality. And this one's solid. One of the biggest mistakes that I see people make on these sorts of problems is forgetting the fact that we have a dotted line. This one's solid, but the other one was dotted. Lose points if you give me not a dotted line. Alright, the grid inequality says greater than or equal to, so which way will I draw my arrow when I go to my boundary? Above, and the arrow went into this half plane, so that means this whole half plane is my solution set. So I will shade this region. And there's the answer. So this lovely story problem comes straight out of the book. The map shows the number of tickets needed for small or large rides at the fair. If you've ever been to a fair that has rides, you know that you have to buy a certain number of tickets for each ride. You do not want to spend any more than $15 on tickets. How many small or large rides can you ride? So the grid there suggests that we're going to have to graph some sort of inequality, which we're not given, which means that we need to come up with one. So we need to define some variables since we're about to come up with an inequality. What should we call our variables? This is actually 25 cents right there. We need some variables. S and L. Okay, so S will be small rides, and L will be large rides. What about small and large rides? No, I mean like with our variables. Is this the cost of a small ride? What is it? No, I mean specifically what does S represent? Not just small rides. No. I'm just defining variables right now. What does small rides? What about small rides? Is it how much the small ride costs? How many tickets does it take to ride a small ride? Are those variables? What are we looking for in this problem? How many small rides? So S should represent what? The number of small rides, yeah. It's important to realize that we're talking about the number of small rides and the number of large rides. It's not just small rides and large rides. That's an important distinction because we're also talking about money in this problem. And this variable has nothing to do with money. This variable has nothing to do with money. But we are very concerned about money. Okay, so we do need to make that distinction, and this will come into play in Chapter 3 a lot. So make sure you really understand what that variable is. Okay, so we need to come up with an inequality. I'll get you started. We don't want to spend more than $15 in tickets. So here's my $15. And how can I say that I don't want to spend more than $15? Yeah, it's 25 cents a ticket. So how can I say I don't want to spend more than 15? So my inequality will have to be less than or equal to 15. Whatever I do over here, it better wind up being less than $15. That's what this sentence right here is saying. All right. Now, with our variables, let's come up with an expression on the left-hand side that completes this inequality. Okay, so it's tempting to say 3s plus 5l is less than or equal to 15. It's tempting to do that, but what's wrong with this? No. How many rides? You're on the right track. The rides are not money. This is dollars. This is a number times a number. That's not dollars. My units here don't match up. Okay? So you're going to have to watch out for your units here. A small ride does cost 3 tickets, but 3 tickets is not what I need. What do I need? The amount of money it costs to ride that small ride. How much does it cost me to ride the small ride if tickets are 25 cents a piece? 75 cents. So actually I need 75 cents, 0.75 s. And then what does the 5L turn into? Good, $1.25 per large ride. So 1.25. Now I am in terms of money. So this is now a good inequality. Okay, so we want to graph this. Where should I put my origin here? Bottom left. Why? Yeah, we're never going to write a negative number of rides. So here's my origin. And now this is a graph, so we need to figure out what goes on the horizontal axis and what goes on the vertical axis. In this case, does it necessarily matter? Does the number of large rides that I ride dictate the number of small rides that I ride? Or vice versa? No, it doesn't. So I can put whatever I want on either axis on this problem. What do you want to put on the x-axis? It doesn't matter. Small. Okay. Small. Which makes large rides on the y-axis. Now, if I want to put this in slope-intercept form is y greater than or less than whatever, or equal to mx plus b, right? But it starts with y. So, what do I need to solve this inequality for here? Got to solve for a variable. Normally I'd solve for y, but y in this case is L, so therefore I need to solve for L to be in slope-intercept form. So I'll subtract 75s from both sides. And I have 1.25 L is less than or equal to negative 0.75 S plus 15. And then divide everything by $1.25. And we have L is less than or equal to, it stays less than or equal to because I didn't divide by a negative number. Looks like a challenging fraction right there. What is negative 0.75 divided by 1.25? What is it? 0.6? Okay, what is that as a fraction? 3/5. S. 15 divided by 1.25? Plus 12. It should be negative, thank you. Okay, so now we can graph this thing. We have a 14 by 14 grid here, so I don't think I need to change my scale any. I go up 12, that's right here, there's my y-intercept. So I can ride 12 large rides for $15. And then I have a slope of negative 3/5. I need to go down 3, 1, 2, 3, over 1, 2, 3, 4, 5. Down 1, 2, 3, over 1, 2, 3, 4, 5. I am going to wind up off my scale here. Down 3, 1, 2, 3, 4. So I'd be like right there. There's my graph. Dotted or solid? Solid. And shading which way? Which way? Yeah, less than says below, so that would be underneath the graph here. So all of this you'll learn in chapter 3 is called something called the feasible region. Every value inside here works. I can ride 12 large rides, and 0 small rides. Or just pick out any ordered pair anywhere inside the feasible region. I can ride, let's see, that'd be 1, 2, 3, 4, 5 small rides and whatever large rides. Okay? Everything in here works. So how many small or large rides can you ride? This is the answer. Any one of these ordered pairs. I can ride 12 large, no small, or I can ride here, I don't know what that would be, 10 small and maybe 5 large or something like that. But every one of these works. This is what we're going to be doing in chapter 3 all the time. So a story problem like this definitely has importance.